So 6.
Yes, that's number 6 in our chart. Exactly. Yes, thank you. Thank you. Good. I can't get away with anything in this class. And I want to thank everyone who shared their experience. And again, I commend you for doing so well. Okay, horizontal stretching or shrinking. Let's start with f of x is x cubed. We committed to memory. This function was committed to memory some time ago in transformations. And here was the graph, and we used it for symmetry when we talked about which type of symmetry. Very good, symmetry with respect to the origin. Now, please notice one thing. When I graph x cubed, you see what happens here at the origin? I need this for chapter 3. It's not for now, but I would like you to see it from now. See what happens here? It takes its time till it gets to the origin and then moves away from the origin. This is a totally different type of intercept, x-intercept, right? This is a straightforward, like fast. This one is not fast. It goes slow, slow, slow. There is only one x-intercept, not more than one. But it approaches it not directly, but slowly. So keep this in mind. I'll remind you, and we'll discuss it in chapter 3. Okay, now the next question I have for you is, how do I determine f of twice x? We know how to determine this because we know how to evaluate a function. The function says f of whatever equals whatever cubed. So now I would like to determine f of twice x. Before you say anything, I'm going to ask you, what am I changing? Am I changing x or am I changing y? Okay. Every time we talk about horizontal, anything horizontal, what am I changing? Right. If it's horizontal, it must be x. If it's vertical, it must be good. So let's start again. I'm changing x into twice x. So it's obviously something that happens horizontally. Good. So now please tell me how do I get this function? What do I have to do? Very good. Awesome. Indeed. 2x cubed. F of whatever is x cubed, so now it's whatever cubed. Good. So now, how do I simplify this? And let me caution you, this is not a sum. This is not a binomial. So don't say 3 terms. This is just one product. One factor and another factor. So we're not applying that special product. So what is it? So what do we have to do here? Let's analyze this. Yes, which is good and very good. This is indeed correct. Okay. Now stay with me. Don't look at this for a moment. And let's write down something very important. And a note for ourselves. This is a transformation on x, not on y, correct? Not y. What did we do? We changed x into very good, 2x. Okay. Now forget for a moment where this is coming from, and let's just look at this function. Because I would like us to draw a conclusion. I don't want to just give you the result. Here it is. Memorize it. I don't want to do that. Okay. So now let's look at 8x cubed. So this is x cubed. This is a transformation we've known for a while. So this is x cubed. What does 8x cubed do? This, horizontal shrinking, or vertical shrinking, or vertical stretching. Is that clear? It's the 8, the number 8 in front of the function. It's not 1/2. So 1/2 would have done this. I'm multiplying all y values by 8. So if I multiply all y values by 8, this is a vertical stretching by a factor of 8. Are you with me? So then I'm asking you now, I'm connecting the beginning to the end. And I'm going to ask you, when I change x into twice x, don't say anything just yet, x into twice x, this is what happens. But I need to know what happens horizontally. Exactly. It's a horizontal shrinking. Would you have expected that? If you change x into twice x, would you have said, oh, it's a horizontal shrinking? Not really, right? So this is the most difficult one to understand. Okay? So when we change x into twice x, the graph shrinks horizontally by a factor of 1/2. Okay? So this f of twice x is a horizontal shrinking by a factor of 1/2. Now we can fast forward, and if you give me an example, or I give you an example of f of 1/3 x, what will this represent? If twice x is a horizontal shrinking of the graph, what do you think 1/3 x will do? Yes, it's a horizontal stretching of the graph. So the graph will do this. Okay? So this is a horizontal stretching by a factor of, excellent. Very good. Indeed, by a factor of 3. And this is it. Now I would like to apply this in one problem, and then we can move on. And let's say on page 295, I would like to look at both 49 and 50. So 49 and problem 50, again on 295. In 49, we have g of x is twice f of 1/2 x. And in 50, we have g of x equals 1/2 f of twice x. And now you can say, wonderful, but where is the function? Here it is. We have to copy it. So let's copy the graph. It's not a difficult situation. I'll give you the points. -4, -2. 1, 2, 3, 4, 1, 2. -2, 0. 0, 2. 2, 2. And 4, 0. So here's the graph. We're not given it the expression. We're only given the graph f. So this is -4, this is 4, 2, -2, and so on and so forth. So let's work on problem 49 first. I have to present the first transformation. What is the first transformation in this? In order of operations. Say it again. Yes, I have to write f of 1/2 x. Good. What does that do? When I change x into 1/2 x, it's horizontal, obviously. Is it this? Or is it this? Yes. So this is a horizontal stretching by a factor of 2. Awesome. Transformation number 2 is on transformation number 1, which is twice f of 1/2 x. What am I changing now? What am I changing in 1 to get 2? And the answer is either x or y. I have to decide. But since I'm not changing x, and this is a number completely outside of the function, it does not touch x, it must be a transformation in y. So what will I do to this graph to get this? Right? By a factor of 2. Vertical stretching by a factor of 2. Vertical by a factor of 2. Okay, let's graph the first one. First, you told me to stretch the graph by a factor of 2 horizontally. Ready? I look at few points, and the key points are 1, 2, 3, 4, 5. It's sufficient. For each point, I will change the x coordinate, multiplying it not by 1/2, but by 2. This point has the x coordinate at -4. Y does not change. We only stretch the graph horizontally. Where does this point go? Still at -2 for y, but where will its x be? Thank you very much. Now, this point has x at -2. Where will it go? This point has x0. Where will it go? The answer is nowhere, because 0 multiplied by 2 is exactly. This point has x equals 2. Where will it go? At the same height, but at 4. Where will this point go? So here's the graph of f of 1/2 x. F of 1/2 x. Now, final step that you already gave me is vertical stretching by a factor of 2. Now the transformation is on y. I'm looking not at the function, but at the blue graph. So right here, the height is at -2. Vertical stretching by a factor of 2. Where will this point go? And this is what happens when you don't plan ahead. So now I don't have room. I'm going to squeeze it in right here. This point has a height of 0. Where will it go? Nowhere, right? This point has a height of 2. Where will it go? This point has a height of 2. Where will it go? And this point has a height of 0. Where will it go? So this is the final graph of twice f of 1/2 x. But it has to be presented in the order of operations. Say it again? Exactly. So the orange graph changed into the blue graph by horizontal stretching. The blue graph changed into the green graph by vertical stretching of a factor of 2. Does it make sense? Okay, so should we do the other one, or is this good enough?
We'll do the other one.
Okay, very good. I have to graph the function one more time, because I don't want to put both on the same coordinate system. So let's graph it. Not difficult. So -4, 2, 2, 0, 0, 2, and 4. Good. So this is function f. And now we want to graph g of x, which is 1/2 f of twice x. What is the first step? Yes? Careful. 1/2. Right. So the first step is f of twice x, which is a horizontal shrinking by a factor of 1/2. And number 2 is a transformation on number 1. So that will be 1/2 f of twice x. What will this do to the graph of 1? Vertical shrinking. We are multiplying the y values by 1/2 now. That is not the opposite. Only this one is the opposite of what you would have expected, but this one is straightforward. So it's a vertical shrinking by a factor of 1/2. So I have to start with the first one. Let's do it. So this is a horizontal shrinking by a factor of 1/2. This point is at x equals -4. Where will it go?
-2.
Correct, right here. This point is at x equals -2. Where will it go? Say it again. X is -2. -1, correct. This point has x equals 0. Where will it go? Oh, I'm sorry. Yes, nowhere is the correct answer. This point is at x equals 2. Where will it go? Yes, right here. And this point is at x equals 4. Where will it go? So this is f. I'm sorry?
And this is because we're multiplying each point by 1/2.
The x coordinate. Horizontal. Only the x coordinate. I'm not changing y. Only the x. Better? Okay. Good. So now, last transformation. And this is on y. And it's a vertical shrinking by a factor of 1/2. This point has y -2. Where does it go? -1. This point has y 0. Where does it go? Stays. Very good. This point has y equals 2. Where does it go?
1.
Very good. This point has y equals 2. Where does it go? Good. And this point has y equals 0. Where does it go? Very good. So this is the final graph.
I don't know what this point is, but
So this is 1/2 f of twice x. I think we got the idea. Now, if you decide to take trigonometry, then I will have plenty of functions to show you with this transformation. But I don't have ready any particular type of function for this. Like from the basic ones, this list of 7, I can't illustrate it with this. Okay, so that's why we are given graphs to apply this transformation. Okay, so this is the end of 2.5. Let's move on to 2.6. 2.6 is a review. However, we're going to go over everything. Number 1 is the algebra of functions. That's the first topic. Algebra of functions. And the second topic, well, what is algebra? Adding, subtracting, multiplying, and dividing functions. And the other option of creating new function is called function composition. So we have 5 different ways of creating new functions. Any questions so far? I don't want to forget to return your tests. I like carrying them back and forth. Thank you. Okay, so can anyone give us 2 functions? Let's say a linear and a quadratic. So we can illustrate the algebra of functions first. Adding, subtracting, multiplying, and dividing functions. Do you think I still need this? Okay, no, I think I'm okay. Good, much better. So, a function f of x, please, and a function g of x. You can select from the book if you want. I can tell you where they are, or you can just give me a function.
2x plus 1.
Awesome. What type of function is this? Perfect. And let's also look at a quadratic. I would like to change this one into quadratic, and you'll see in a moment why. So let's say it's this. So now let's determine a linear. Let's use a linear function.
X minus 1.
X minus 1. It couldn't be nicer. Perfect. So let's suppose we want to create a function by adding these two. The function notation will be f plus g of x, which is self-explanatory. So if I ask you find f plus g of x, if I give you two functions, you're not going to ask me how, because it's very clear, right? So what do? What do I have to write?
2x squared plus 1.
Yes, but I have to write, you're right, you're way ahead of me like always, but I have to write the definition for everyone to see. So f of x, I'm sorry, f plus g of x must equal f of x plus g of x. And yes, now I will replace f of x plus, I will replace g of x, and I get in descending order 2x squared plus x minus 2. What does this function represent? It's a new function, totally new function that was determined by adding the first two. Okay. Now, if you're asked to find f minus g, what do you think you're going to do?
X minus 1.
I copy f of x again, 2x squared minus 1, but now I have to be careful. Careful for what? Yes. So what do I write? Very good. These two go away, so I get 2x squared minus x. What does this represent? It's a new function determined using f and g by subtracting them. Any questions? Okay. Yes.
Why do we have 2x minus 2x squared minus 1?
It's 2x plus.
Oh. I'm sorry.
Wait, what?
No, I copied 2x squared minus 1 instead of 2x squared plus 1. And maybe I should change this one instead, but that's okay. Yeah, let's change that one because otherwise I have to change more. Sorry about that. Thank you. Thank you, Joseph. I appreciate it. I just copied it wrongly. So then I'm going to leave it as is, just change the original function. So I don't have to, because otherwise I have to change way more. So these two don't go away. Okay, so nothing else changes, just the original function. Okay, so now this is a totally new function obtained by subtracting the previous ones, the given ones. What about fg? What do you think this says to us? When we talk about fg, what is that? Yes, so how do I write it? Obviously, of x times, very good, that's it. I copy f, which is 2x squared minus 1 after my mistakes, all right, and multiply by x minus 1. I have to distribute, combine like terms, so on and so forth. So this is 2x cubed. I prefer distributing from here. You choose your own method, it doesn't matter. Minus x, and then minus 2x squared, and then plus 1. So in descending order, I have 2x cubed minus 2x squared minus x plus 1. What is this? This is a totally new function, was obtained from the given functions by multiplication. That's it. Perfect. Now, can anyone tell us what type of functions are these? Not yet. They are obtained with a sum and difference and product. But since this is quadratic and this is quadratic and this is cubic, there is a big umbrella of functions. Very good. Awesome. We're going to deal with this in chapter 3. So all these are polynomial. they have a very specific property. What is that main property? They have more than one, but what is one very important property that we should remember always? Their domain is all real numbers always. So let's put that as a note. Note, polynomial functions have domain all real numbers. What I like to call friendly functions. Okay, so obviously you will say the domain of this, the domain of this, the domain of this is very good. All real numbers. Okay, we have one more function to look at before we look at the fifth one. Fifth.
Awful.
Which one?
This one you're about
Why? So what does this equal to? And this is something I have not done for the previous three. I have to put an if. If what?
They equal real numbers?
No?
They equals a real number.
No?
Yeah.
What? Elaborate.
X cannot equal 0.
X is not in the denominator. Something else is in the denominator.
Oh,
But you are on the right track. So what cannot be 0? Which is? Indeed. We know this from what? From solving what type of equations? What type of equations?
Oh.
Exactly. What type of equations?
Radical.
No. Exactly.
Rational.
From rational equations, we know that the denominator can never be 0, correct? Good, very good. So now please tell me what to write. I copy the top, which is 2x squared minus 1. I copy the bottom, which is x minus 1. And now I'm ready to write if this function will exist. If x does not equal 1. And now for this function, since we established the domain of all the other ones, I would like you to give me the domain of f over g. Very important for the next chapter. Yes. What will be the domain of this function? We've done this before. Yes. Except. Except. Yes. How do I write that? Exactly. Very good. Union. That's it. So this is the domain of this function. In other words, in plain English, everything but 1. Well done. Okay, let's look now at the what it's called the common domain. Before we continue, what does the common domain mean? So let's look at the graph of two functions. I'm going to graph this function, let's say between -5 and 4. And I'm going to graph this function between, let's say, -2 and infinity. So this is function g, and this is function f. And I am going to ask you a couple of questions. How much is, no, I didn't mean that. How much is f plus g of 0? How do I determine f plus g of 0? Tell me what to write and I'll write it, if it's correct.
F of 0 plus 0
Of course, that's exactly what we just did. Thank you. So this must be f of 0 plus g of 0. We did the same thing with x. Well, it has to be the same thing with 0. Perfect. So I will say, I don't know, let's say they cross here. I'm going to say that this is 3. How much is f of 0? How much is g of 0? 3. So how much is f plus g of 0? Very good. Awesome. Now I'm going to ask you a different question. Please find f minus g of 7. So what do I have to write first?
F of 7
Yes,
minus G of 7.
perfect. And now let's look at the graph. What do you conclude? F of 7. So this is 4, 5, 6, 7. How much is f of 7? How do we call that? Exactly. But we like to say undefined. But the answer is it does not exist. The function f is not defined at 7. I don't care if g is. If one of these two functions is not defined at a point, I cannot determine this. It doesn't exist. So now we understand what the concept of common domain is. So can anyone give us the common domain of these two functions? Where I can ask you to find the sum, the difference, the product, and the ratio for whatever.
Between -2 and 4.
Thank you very much. Common domain is between -2 and 4. So if I wanted to evaluate the sum, difference, product, or ratio, I'd better pick a number, an x value between -2 and 4. Because if I pick outside of this interval, you would say what? Sorry, I can't create your function. Or I cannot give you the function value. Correct? So this is the common domain. Now, we can continue with the last type, which is slightly more difficult to understand, and totally different than what we've seen before, which is called function composition. Function composition. Ready? Let's look at 3 bubbles and explain what this means. Say it again. I just couldn't hear you.
I said they're circles.
Okay, let's look at 3 circles. I accept that. And let's say I have here a point, an x value, which is x equals 3. And let's say I want to apply a function that is g. What will I get? I have x equals 3. I want to apply function g to it. What do I get? Of course, I have g of 3. We know that. This is nothing new. Now, this is a number. Whatever number you want, it doesn't matter. But let's suppose to this number, I would like to continue to apply this time a function f. Can anyone give us what the result will be? You cannot give me a number. You can just say it must be perfect. It is f of g of 3, correct. So this notation, in other words, f of g of x in general, is denoted by f, a circle, tiny circle g, and here's how we read it. F comp g, or the composite of f and g.
Wait a minute. Hold on. Let's rewrite this. F circle G.
It's f comp g, the composite of f and g. Okay. Let's go back to the balloons, circles. and talk a little bit more about this. Forget about function f for a moment, and I would like you to tell me, what does this set represent for function g? I'm taking x, say it again.
The X value.
Correct. How do we call it? Awesome. How do we call that set? It has a special name. No, the set where we pick x from.
The domain.
Domain, very good. So this is the domain of G. Awesome. Now, can you please tell me, what will this represent for G?
Range.
Very good. It's the values of G, is the output, so it must be the range of G. Good. Now forget about G for a moment. And please tell me, what will this represent, this set represents for f? Set for a function f. Exactly. So this is also the domain of f. So this circle here has two properties. One is the range of G, and the other one is the domain, at the same time, the domain of f. What can go wrong? When we create a function composition, we do not ever talk about a common domain. The two functions don't have to have a common domain. If they have, it's fine. If they don't, it's fine too. But this is the potential problem that will break the chain, that I will not be able to determine the function composition. What could the problem be? That I'm bringing a number in here that I cannot apply f to. In this class, we are not asking you to determine the domain of the function composition, but I'm just pointing out what could go wrong. So what can go wrong? That the range of G and the domain of f do not work well together. That will break the chain. That's all I was going to say about that. Okay, so let's look give us a function, and you want a function f and a function g, so we can illustrate the function composition before we look at a problem from your book. Let's say x is negative 2x plus 1, and f is
3x minus 1.
let's say 3x squared plus x. So we want to find f comp g. We have to write the definition first. Can anyone dictate what f comp g represents? F of
3x.
indeed. So coming back here, the name of the first function we apply to x is inner. It's the inner function. It's the function that we apply to x first. Well, what do you think the function f will be after we apply it to this value, which is g of 3? The outer. So the first function we apply is the inner. The second function we apply is the outer. So one more time here, which one is the inner and which one is the outer in the f comp g? Say it again. Indeed, because I have to evaluate g first. So we're not given values. We are trying to find the function. You don't have to erase this. I'm just making a point. What do I replace this by? Very good. G of x, negative 2x plus 1. So this is f of negative 2x plus 1. Now stay with me. This is very important. We know this from the previous chapter. This is not new. Now I'm looking at f. Function f says this to me. 3 multiplied by whatever squared plus whatever. This is my whatever now. So please tell me what to write.
3 times negative 2x plus 1 close parentheses. Isn't it squared?
Thank you.
Right? Okay. Plus -2 x plus 1.
See what happens once you see it and you understand it, you will not forget it. Would you agree?
I mean, I don't know about remembering it, but
I am sure you will remember because you understood it. Okay, so then we have to continue simplifying this. Bless you.
excuse me.
So
thank
that's
you.
not done. 3 stays outside. What do I do next? First day of classes, be careful what you say. Very good. 4x squared, I agree. Minus. Yes. Plus 1. I don't need parentheses here anymore, so this is -2x plus 1. And now I can distribute. Only now I can. 12x squared minus 12x plus 3 minus 2x plus 1. And in descending order, 12x squared minus 14x plus 4. What does this represent? Yes?
Wait, but take it back. That's what should we distribute the addition sign?
The addition sign doesn't change anything.
Or would it? Because
Positive 1 times -2 is -2.
Yeah. Okay. Wait. Okay. Yeah.
Okay, any questions here? So what does this represent? It represents the function composition of f and g, where g is the inner function and f is the outer. We would like now to determine g comp f. What does this say? What do I have to find now, and what is the answer for now? How do I present this? G of, indeed, I have to write that first. Now I will replace this by, very good, 3x squared plus x. Now I have to look at g, and I have to perform the operations that g is requiring. G requires -2 times whatever plus 1. So,
-2 times 3x squared plus x plus 1.
that's it. So now, by the order of operations, I can continue by distributing. So this is -6x squared minus 2x plus 1, and this is done. And this is how we determine the function composition. You will not be asked to determine the domain of the function composition, but you will be asked to determine the common domain when we add and subtract, multiply, or divide.
You said we won't be asked to do this?
You will not be asked to find the domain of the function composition. I didn't show you. I only showed you that if those two sets don't work well together, then you cannot create the function composition. Okay. Any questions? Any questions here? Okay. So in summary so far, we know that we have 5 different ways of creating new functions. And they are adding, subtracting, multiplying, dividing functions, and then function composition. Okay. I would like to look at a problem from your book in which we are not given the functions, but we are given their graphs. So let's take a look. On page, this is in 2.6. I'll find it. Okay. On page 311, let's look at problem 94. And here it is. We're asked to find the g comp f of -1. We don't have g, we don't have f. We have to write what this means first. So what does this mean? G of, perfect, very good. Where is my starting point? No, my starting point is, indeed, this piece. I need to replace this piece by what it equals to. So I'm looking at the graph because the function is not given to us. I can plug in -1. So when x is -1, these are the graphs. This is the blue graph is f, and the purple graph is g. So I have to find f of -1. So here it is. Can anyone give us f of -1? Very good. Do we all see f of -1 is 1?
It's kind of hard to see.
So it's right here. So it is 1. So then, what am I asked to find? G of 1. Now let's take a look. Now I look at the purple graph, and I determine G of 1. Ready? The purple graph, and we want to find G of 1. Indeed, -5. Very good. So we determined the value of a function composition without even having the functions, but we were given the graphs. So we read from the graphs all these values. Very good. Now I would like to ask you this question. It's called function decomposition. Let's say we have f of x equals 1 over x squared plus 4. And I would like you to create two functions, one that is inner and one that is outer, such that when I create the function composition, I get the original function. What do you think? There is more than one correct answer here. What will be the first function that you apply to x? If you want to evaluate this function for x equals 10, where would you look first? Okay, look at this function and imagine that you evaluate it for 10. What will you do first? Yes, so which function would you, no, you cannot start with the outer, you have to start with the inner. So give me an example of, in this case, of which function will you apply to 10 first?
X squared plus 4.
That's it. The inner function is x squared plus 4. Then you get a number. Once I replace x by 10 square and add 4, I only get a number here. Which function I apply to this number now? That's it. So the inner function is the first function that I would apply to x, which is x squared plus 4. And once I get a number, I divide 1 by that number. Let's try another function.
What? That I don't understand, like any of it.
So if I have to find f of 10, I have to evaluate x squared plus 4 first, which means 10 squared plus 4. I get a number. When I'm done, this becomes a number. What function I apply to this number? 1 over x. To get f of x. Let's do another. You'll see in a moment. So let's say I have f of x, which is the square root of 2x minus 4. Again, I would like an inner and an outer. All you have to do is think in terms of evaluating. Which portion of all this will you evaluate first? That will be your inner. Of course, I don't have a choice. I have to evaluate 2x minus 4 first. And then when I'm done and I get one number here, just a single number, which function I apply to that single number? That's it. That's all it is. So what did we accomplish here? We decomposed the function into two functions. So we guarantee now that this comes this because this is the inner. This comes this will be exactly, let's check. I'm going to call this g of x, and I'm going to call this h of x. I cannot use f. So let's determine h comp g of x. This is g, and this is h. How will I write this? What is the definition? h of, very good. So I start with the inner. I replace g of x by, very good. So this will be h of 2x minus 4. And now I have to look at the outer that says the square root of whatever. So what do I write? That's it. So that was the function we started with. We created an inner, we created an outer, and when we create the function composition, we go back to where we started. That's what we call function decomposition. We can choose another if you want. They're on page 311. So let's say 76, h of x equals 2x minus 5 to the third. And this really helps us understand the function better. Again, I would like you to come up with an inner and an outer. Again, you will only think in terms of evaluating the function. So what is the inner? Right. And what is the outer after I get one number? This is it. So the inner must be evaluated first. When I have a number here, then of course I apply x cubed. And we can go on forever for any function. I can say that all functions are function composition.